Welcome everybody to the webinar of today. The speaker of today is Manuel García-Villalba, and he's going to talk about fluid structure interaction in some bio-inspired problems and numerical study. So as usual, I introduce the speaker very briefly and then I leave him the floor. Manuel García-Villalba is a professor of computational fluid mechanics at the Institute of Fluid Mechanics and Heat Transfer at TU Wien in Austria since 2022. Previously, he was associate professor at Universidad Carlos III de Madrid in Spain, and has also worked at the Karlsruhe Institute of Technology in Germany, where he also got granted his PhD. His research focuses on computational fluid mechanics and its application in engineering and biomedicine. So it's with great pleasure that we have here today Manuel García-Villalba for the seminar of today. So Manuel, I just stop sharing my screen and you can start sharing yours. That's it. We see your screen.
Okay. Great. Okay, so everything is working, right?
Yes, we see it full screen. Thank you.
Okay. So and also you see the pointer, right?
Yes. Pointer options. Yes, the laser pointer. Yes.
Okay. So thank you very much, Francesco, for inviting me, and thank you all for connecting to the Zoom meeting. I'm very happy to be able to present our work on bioinspired fluid structure interaction. I have been now for some time in Vienna, but this work was done with my team in Madrid in the last 5 years. So let me first introduce my team in Madrid. So the work was done supervised by me and also by Oscar Flores, who is a professor there of aerospace engineering. And we were lucky to have a group of very talented people who are now conquering the world everywhere. So our main in-house code was developed by Manuel Moriche, who is now a postdoc in my group, and by Alejandro Gonzalo, who is a postdoc now at the University of Washington in Seattle. And the work I'm going to present today was mainly done by Gonzalo Arranz, who is now a postdoctoral researcher at MIT, and by Cayetano Martinez Muriel, who very recently joined the team of Airbus in Germany. So, as I said, this was a very good team, and they did very nice work. And if you like it, of course, the responsibility is of Cayetano and of Gonzalo. This is the outline of my talk. I will first discuss a little bit about the motivation of our work, and this will be followed by some slides in which I will discuss the numerical methods that we employ in our in-house code. In particular, I will discuss the immense boundary methodology that we use and the multi-body approach. And this will be followed then by the two topics that I have selected for today. And you can see in the images, I will discuss flapping wings in tandem configuration, where the main ingredient that we want to study is the fact that the wings are flexible along the span. And this will be followed by the hydrodynamic interaction between self-propulsed flappers. So, as I said, the motivation of our work is by inspiration, and it goes without saying that insects, fish, or birds, they fly and swim professionally. They are very efficient and they perform very impressive maneuvers. But even simpler systems in nature also are worth studying. For example, we have studied in the past Samara seeds that disperse by using auto-rotation mechanisms. Of course, one can look at the hovering of hummingbirds or at the complex patterns of swimming that the fish perform when they were swimming in schools. And this is why engineers are trying to mimic their the capabilities. And there are many recent devices that are being developed all over the world, trying to take inspiration from nature. I have taken here some of these recent devices, for example, the Delphi in TU Delft, or the Hummingbird from a company called Environment, or the RoboBee in Harvard. I could have taken many others. There are many such devices being under development, but in my opinion, at the moment, they are following the path that took engineering in history in many cases, in which they are trying to fly first, and the theory will come later. So still, there are many processes which are not very well understood. And this is why these devices are still rather clumsy, and they tend to work well in their design point. But as soon as you try to work enough design, the performance is very limited. So in fact, I have found here a couple of videos showing the direct comparison between a dragonfly and a robotic counterpart. And these videos I just found on the net. And you can see how effortless and gracious is the dragonfly, while the robotic counterpart is not at all that gracious, and it looks like it's rowing in the air more than flying. So that the flight is still not so, let's say, so beautiful as the flight of the dragonfly. My opinion, there is a need for an improved understanding of basic physical mechanisms, and that's what we try to do in our group. We try to isolate phenomena, see where we can get some improved understanding of physical phenomena. So let me tell you a little bit about these challenges, the challenges to improve these devices. First, the problem is that all these bioinspired problems are highly complex and very nonlinear problems that involve fluid structure interaction. And there is a strong coupling between the hydrodynamics and the dynamics of the vehicle. The vehicles are usually geometrically very complex. They can have structures that move relative to each other, so that we need to consider relative motion among them. And also, of course, the structures, they might be flexible and subject to large deformations. So that we have a couple problems involving aerodynamics, dynamics, and flexibility. And on top of that, the real problem is that the parametric space is huge. So you can have, even for very simple problems, lots of parameters that are involved. Like if you consider, for example, a couple of airfoils, then you have the Reynolds number, you have the reduced frequency, you have the amplitude of motion, the distance between the airfoils, and one could continue. So that often what we learn in one problem is not directly applicable to another problem. So today I have selected two of the works that we have been doing in our group, and I hope that you get an illustration of the kind of things that we can do nowadays. Before that, let me discuss a little bit about our in-house code, which is called Toucan. And in Toucan, we solve the Navier-Stokes equations of the incompressible flow using a well-established methodology in which we employ a staggered mesh using a fractional step method. The space discretization is based on second-order finite differences. And for the temporal scheme, we use a semi-implicit low storage Runge-Knuth scheme. We have tested our code in many machines. We have shown that the code scales well. And also very recently, we have also ported the code to GPUs, so where we can handle all the problems. So the code can cope with bodies of arbitrary shape in motion, and these bodies are modeled using the immersed boundary method, in particular the one proposed by Ullman in 2005, in which we have an Eulerian mesh in which we solve for the fluid, and then we have a Lagrangian mesh for the objects, and then the coupling between the two is done via a forcing term in the Navier-Stokes equations, in such a way that we fulfill the boundary condition on the surface of the object. As for the motion of the objects, there are in our code several possibilities. One possibility is that we prescribe the motion, and this we have been using in many applications. For example, in our work in cardiovascular flows, that's what we do to solve the flow in the atrium. We impose the motion of the walls of the atrium that we obtain from medical images. Or the motion can be the result of dynamic equations of motion. And actually, we have two versions of the code. We have a version in which we solve for a single body, or more interesting for the talk of today, we have a version of the code in which we solve the dynamics of a multi-body system of rigid bodies. Okay, for this, what we call to come multi-body. In this method, what we use is we took some libraries from the literature using robotic algorithms based on generalized coordinates. And then this leads to a system of ordinary differential equations that involve a generalized inertia matrix and some terms that take into account the relative motion between the objects. And then we have generalized forces, the aerodynamic forces that enter via this term, and the forces due to the links between the objects that enter via this term. The way in which we couple the system of equations is a weak coupling, so that we solve for the fluid and for the multibody separately. So first, we give a time step of the fluid equations using the position of the object. Okay, and from there we obtain the forces, and we then convert these forces to generalized forces, and then we apply them to the multibody system, so that we obtain the next time step for the multibody system. So this weak coupling, of course, is a method that has limitations, cannot be used for all applications, but for the kind of applications for which we have been using it, it's very simple and works pretty well. We have, of course, validated our code thoroughly, and you can find the description of the methodology and of the validation test in this publication in Journal of Research Structures. The two examples I'm going to discuss today are based on flexible structures. So in some situations, it is possible to model a flexible body using a combination of rigid bodies. And in particular, I found this very nice example just by chance in YouTube when I was looking for these kind of videos. And I like it very much because it illustrates very well the kind of approach that we are taking. So what we are doing to model a wing or flapper that is flexible is we split the wing in a number of rigid segments, and these segments we connect using torsional springs. So that if you think about the continuum beam or the continuum wing, the flexible characteristics would be given by the Young modulus, the inertia tensor, and so on. In the discrete system, this is given by the stiffness of the torsional springs. And then to connect these two approaches, what we do is we tune the stiffness of the springs so that we have the same natural frequency of the discrete system, that they coincide with the natural frequencies of the beam. Okay, so that when you have that, you could expect that the dynamics of your discrete system is going to be very similar as the dynamics of the continuum system. And in fact, we are not the first doing this. There is a nice paper by Aurora and co-workers in JFM 2018, where they show that this works pretty well. And with not many segments, I think they have something like 20 segments, they are able to mimic up to the fourth natural frequency of the system. Also, we will use the first natural frequency of the system as a way of quantifying how flexible a structure is. So in particular, we will, instead of using the Young modulus or the stiffness of the springs, I will characterize the the flexibility of the wing by using the ratio of the first natural frequency of the structure compared to the frequency of oscillation. But I will return to this point whenever this comes in the discussion. So with this, let me start by discussing the first example I wanted to discuss today. And it is the flapping wings in tandem configuration where the wings are flexible along the span. The example is loosely based on dragonflies, but of course it's very different because since we are interested in isolating mechanisms, we are not taking the wings of the dragonflies. Instead, we are taking rectangular wings that they are flexible along the span only. Then questions that we are going to address is first whether there is a flexibility of the structure which is related to an enhanced aerodynamic performance. If yes, what are the mechanisms associated to this aerodynamic performance? And if the hindwing benefits from aerodynamic interactions with the wake of the forewing. So these are the kind of questions that we are interested in answering. Here, a bit more details about the problem setup. As I said, we are going to consider two wings made of several segments and connected by torsional springs, that they are flying in forward flight, so with a given flight speed. And we are going to consider wings of aspect ratio 2 and 4. What we do is we impose the heaving and pitching motion of each of the wing midsection only, okay, and the rest of the wing moves passively. So here you have a representation of the pitching and heaving motion of the midsection of the wings. And if you look at this dot that is moving in the screen, that represents the flight velocity, so that you get a visual impression of how fast the vertical motion of the wing is compared to the horizontal motion. Also, we are going to look at wings of various flexibilities. So we vary the flexibility from very flexible to rigid wings. So in a rigid wing, then the ratio between the natural frequency of the structure and the imposed frequency would go to infinity. And then with decreasing this parameter, we have then the increasing flexibility. So this is the main parameter that we are going to change. And other parameters are kept constant. So for example, the Reynolds number of the flow based on the flight speed is, and the chord is 1000. The reduced frequency is this number. The density ratio between the structure and the fluid is 20. This is the thickness of the wing. And this parameter here, the effective inertia, combines the thickness, the density ratio, and the frequency ratio. And the value is 0.1, which is typical for insects. Now, a little bit more about the motion that we have selected. I mentioned at the beginning that the parametric space is huge, so we had to select some kinematics that made some sense. And the way in which we did this is we chose to, via an optimization process, we chose heaving and pitching motion that enhance the hindwing performance in the 2D configuration. Let me explain you this a little bit more. So if you look at the motion of the isolated wing in the 2D configuration, this is just a 2D simulation of the isolated airfoil. So you see that we have a vortex-dominated flow in which we develop a leading edge vortex both during the downstroke and during the upstroke, okay, and that this leading edge vortex travels in the wake. And when you look at the performance, the aerodynamic performance of this isolated wing, then the thrust coefficient that you get is this one, and the propulsive efficiency that you get is this one. Now, when you look at the tandem system, what you observe is that the flow around the forward wing is very, very similar to the flow of the isolated wing, while the flow over the hindwing, of course, is influenced by the wake of the forewing. So what you see is that the hindwing is navigating the the wake of the forewind in such a way that the leading edge vortex that is formed in the hindwind interacts with the leading edge vortex shed by the forewind, and they form a dipole, and this dipole moves horizontally in the wake, forming a symmetric wake in contrast to the wake obtained for the isolated case that was asymmetric. And in this process, you enhance thrust generation, and when you compare the values of the thrust of the forewind and of the hindwind, you see that in the hindwind we get a value which is almost 3 times the value of the isolated case. Also, if you look at these coefficients, this is the thrust coefficient as a function of time for the isolated airfoil, which would be the black line, the forefoil, that would be the red line, and the hindfoil, that would be the blue line. You see that, of course, you get thrust both during the downstroke and during the upstroke, since the motion is symmetric, but that the effect is really felt by the hindwind, giving you a large amount of thrust. So if you want, this is sort of the design of the simulation. We design the motion to observe this effect in the hindwind. And now this is the starting point, and we want to see how is this performance affected by 3-dimensional effects and also by the flexibility of the wing. So in order to do that, I need to discuss first the case of the isolated wing in order to be able to understand what's going on, and then later on I will consider the case of the tandem wings. So if we look at the aerodynamic performance of the isolated wing, so here what you are seeing is first, in this plot, you see the thrust as a function of time. In this plot, I'm going to show you the mean thrust, so the time average of this signal, the mean thrust as a function of the flexibility, where here the flexibility I'm plotting, the rigid wings will be on the right. And now, with decreasing the frequency ratio, we are increasing the flexibility of the wing. And then I will show you some visualizations on the lower part. So in particular, here you have a visualization now of the rigid case, in which you see that this is an instant in which a leading edge vortex has already developed. This is an instant during the downstroke. Okay, but we also see that now, since we have 3-dimensional effects, we have vertical structures forming in the tips, and these 3-dimensional effects result in a reduction of the thrust coefficient if we compare this number to the value that we had for the 2D configuration. Okay, in the 2D configuration, the value was about something about 4.5. And in the 3D case, for aspect ratio 4, we have a value which is somewhat lower. Okay, so now if we add now the cases for the with increasing flexibility, so we see that with increasing flexibility, the peak force is increased, but also is delayed. It happens at later times during the cycle. So that we see that when you look at the mean thrust, indeed, the thrust increases with increasing flexibility up to what we call the frequency, which is very close to resonance, because this ratio is 1 here. And we are going to call this case the optimal case, because as we will see, this is where we get the maximum thrust. And when you go beyond, this would be now the corresponding visualization for this case. And if we go beyond this point, the performance drops dramatically. You see now we get very low thrust. And when you look at the distribution of thrust, you see that is during some portions of the cycle, we are generating drag on the wing, and then this is not able to be compensated by the thrust, so that beyond resonance, the performance of the wing decreases significantly. It is good to see. This is just an instant. Let me show you an animation so that you can see how the vortex develops on top of the wing. And it is not very clear, but what happens if you compare the rigid wing and the optimal wing is that the leading edge vortex develops somewhat later and remains longer attached to the wing, and this explains the peak in performance here compared to the blue curve. No? So this optimal case would be this red line here, and the rigid case would be this case here. And in contrast, you see that whenever you go beyond resonance, that would be this point here, there is barely any leading edge vortex forming at all. But also you see that it seems that the motion of the midsection and the motion of the tip is out of phase. And this is one of the main issues why the aerodynamic performance is so bad for this case. If we add now here the data for the aspect ratio 2, we see that the data fits very well with together with the data for aspect ratio 4, and that the trend that with increasing flexibility, the performance is enhanced until we reach to the resonance frequency, and from there the performance decreases is very clear. And also you see very clearly, if you look at the reed wings, that we get a little bit more force for aspect ratio 4 than for aspect ratio 2 for the reed wings. And this is, of course, due to the fact that the wing tip effects for the smaller aspect ratio are more important. So that a summary of this slide, we can say that the enhanced performance seems to be linked to a fluid structure resonance, and that the development of the leading edge vortex on the wing is highly influenced by the flexibility of the wing. It's also interesting to look at not only at the aerodynamic performance, but also at the structural response to understand a little bit better what's going on. And what you have here on the left is the deflection of the midline of the wing, so the point with respect to which we perform the pitching. And the cases are the rigid is in blue, the optimal case is in red, and the very flexible case is in black. And you see how for the optimal case, when the wing is moving up, indeed the tip is also moving up, while this is not what happens for the very flexible case, which, as we already sort of showed before, that they are out of phase. So that when you plot here in this image the values for the tip displacement compared to the amplitude of hip in motion, we see that, of course, for rigid wings, nothing happens because the wings are rigid, they don't deform. But with increasing flexibility, we again get a peak which happens at the resonant frequency, and beyond there, this value decreases. And this reinforces the idea that the enhanced performance is related to a resonant phenomenon. Now, I find very useful to look at the envelope of these lines. And when you do that, here I'm plotting the envelope of these lines just from the midline here to the tip. And here again, this is the midline and this is the tip. And you see that for the optimal case, the envelope is such that the amplitude of the tip is larger than the amplitude of the root, opposite to what happened in the case of the very flexible wing. That although the wing is more flexible, you see if you follow one of those lines, you will see that the amplitude between tip and root is larger than the amplitude between tip and root here, but it's not happening at the correct times. So that the timings are very important in order to have this development. And this, from the aerodynamic point of view, is very useful because what we are getting is more amplitude of motion near the tips, and as a consequence, more force. This can also be analyzed in terms of effective angle of attack. In aerodynamics, typically, you relate the angle of attack of a wing to the force generation. So the larger the angle of attack, the larger the force. And here, of course, when you consider heaving and pitching, you need to take into account the motion of the velocities of heaving and pitching, and then you look at something called the effective angle of attack, and then you get a formula like this. And I'm plotting here this quantity for all the cases. So the rigid case would be this case, and going to the left, we increase the flexibility. So I'm plotting here this quantity as a function of the span in the x-axis and in time in the vertical corner. So that, for example, if you look at the rigid case, starting from the bottom, you would have the downstroke until here, and then you have the upstroke. And of course, since the wing is rigid, all the sections have the same effective angle of attack. Now, with increasing flexibility, you see, for example, looking at the downstroke, that the effective angle of attack tends to increase towards the tips. So, and it keeps on increasing, but now it comes to a point in which this increase happens out of synchrony, so that the timing of the events is very important. So at resonance, the tip displacements increases the effective angle of attack, but keeping the synchrony with the wing pitching. And this synchrony leads to the increased thrust. While when you go beyond resonance, the synchrony is lost and the performance is dramatically dropped. So that we see that for the isolated case, the enhanced aerodynamic performance we can see as a combination of resonance, fluid structure resonance, and aerodynamic tailoring, so that the aerodynamic happens, so the fluid structure interaction is such that the aerodynamic response is optimal. Okay, and now you may ask, okay, and what happens with the tandem wings? Are these effects still the same? So here, let me start by showing you a visualization of the flow. So you see here, this is actually the case with optimal, with resonant flexibility. So you see how we developed the leading edge vortex in both airfoil, in both wings, and how, of course, the interactions in the hind wing are far more complicated than the flow structures in the forewing, and also you can see the wingtip effects. And we can try to relate this, at least qualitatively, to what happened in the 2D configuration. So if you recall, when I showed you the two-dimensional movie, we saw all this leading edge vortex, and then the interaction between the leading edge vortex of one wing and the other wing, and finally this forming a dipole. So you can actually sort of see these things also here. So if you look at here, this would be the leading edge vortex, this would be the two vortices that are interacting, and now finally, this is the dipole that is in the wake. But of course, when you go towards the tips, you see that the interactions are much more complicated. You develop tip vortices that, of course, interact with the vortices, and they lead to very complex vertical interactions in the wake. Now, when you look at all the cases, here I have a visualization from the top. Again, here you have rigid wings on the right and increasing flexibility towards the left. We observed that in the forewing, in all cases, we have a very clean leading edge vortex, except, of course, for the case in which we have a very flexible wing. And it is very little affected by the presence of the hind wing. As we will see, the forewing actually behaves as if the wing is isolated, but the hind wing is strongly affected by the presence of the forewing. So we want to see how much is this effect. So what is the role of what we call the wake capture? So here in this plot, I'm showing you the aerodynamic performance. Again, as before, we have the mean thrust coefficient as a function of the flexibility. So the rigid wings on the right going to the left to the very flexible. Here with closed symbols, I'm showing you values for aspect ratio 4, and with open symbols, values for aspect ratio 2. And then the gray symbols are the isolated wing, these ones. The red symbols are the forewing, and the blue symbols are the hind wing. So first, if we compare the forewing and the isolated wing, we see that the trends are very similar. So we see that, as expected, they behave in a very similar way. The values for the forewing are somewhat above the values of the isolated case, but this is an effect that we already observed in the 2D configuration. So this is not something related to the flexibility. It's something that already occurs in 2D. Of course, if you remember, we designed the case so that the performance should be enhanced for the hindwing. So of course, it's more interesting to look at the data for the hindwing. And in order to do that, you need to compare now the blue symbols and the red symbols. And if you start by looking at these two cases, you see that the wave capture phenomenon is very clear. So for rigid wings, we see this wave capture. We get more thrust for the hindwing than for the forewing, and also for intermediate flexibilities, this effect is still visible. However, this effect of the wave capture is lost for the resonant wings and also for the very flexible wings. And in fact, the most interesting observation from this plot is that the enhanced performance now doesn't happen at the resonant frequency, but for the hindwing, the enhanced performance happens out of resonance. This is also visible if we look at this at the structural response, as we saw before. So here again, I'm showing you the flexion patterns in the midcourt, and on top you have the values for the forewing. On the bottom you have the values for the hindwing, and while for the forewing we observe the same phenomenon as before, that the resonant wing has the tips with enhanced amplitude. For the resonant wing in the hindwing, this doesn't happen anymore. And in fact, it is more aerodynamically better to have the structural deformation like the intermediate case. So that the interplay between the wave capture and the structural deformation is not optimal for the resonant case. So it happens that we obtain the enhanced performance with less flexible hindwings than forewings. So this observation gave us the idea that it might be possible, perhaps, to design tandem systems with different flexibilities, and that these tandem systems might outperform systems with the same flexibility. And in order to test this hypothesis, we did a new set of simulations in which we ran nine simulations with aspect ratio 2, with all combinations of frequencies from rigid, intermediate, and resonant flexibility. Okay, so that we did resonant, rigid, resonant, intermediate, and so on. Okay, so we did in total 9 simulations. So first, if we look at the thrust coefficient of the forewing as a function of the frequency, and then this would be now rigid case. This would be the intermediate, and this would be the resonant. You see that the thrust of the forewing is very little affected by the change in flexibility of the hindwing. So the data more or less collapses, and we get that the aerodynamic performance of the forewing is essentially independent of the aerodynamic performance of the hindwing. This is sort of what's expected. And of course, it's more interesting to look at what happened for the hindwing. So here I'm plotting the thrust coefficient of the hindwing as a function of the frequency. And the colors represent the flexibility of the forewing. So first, look at the case of the rigid hindwing. So if the hindwing is rigid, we get more thrust with increasing flexibility of the forewing. Okay, so this is because with increasing flexibility of the forewing, we observe that the vortices that are shed in the wake are more intense, and this leads to a higher thrust coefficient in the hindwing. Okay, this is the first observation. So second observation is now, if we look at the flexible hindwing for a rigid forewing, that would be the blue dots here, okay, we see that with increasing the flexibility of the hindwing, indeed, the performance of the hindwing improves. But this doesn't happen in all the cases, and it turns out that the optimal configuration occurs for the resonant forewing, will be the red case, at the intermediate flexibility for the hinging, sort of confirming the hypothesis that we have. So in summary of this part of the lecture, I have shown you that there is indeed an optimum flexibility, which is associated to an enhanced aerodynamic performance. For isolated wings, we observe that this enhanced aerodynamic performance is a combination of resonance and what we call aerodynamic tailoring, but that for the hing wings of tandem systems, the enhanced performance does not occur at resonance, and there is a balance between the aerodynamic tailoring and the wake capture. So in other words, the timing of the events is extremely important. So this has led us to a new hypothesis that might be beneficial for tandem systems to consider different flexibilities. So you can find much more information about this in these two publications. One is already published, the other one is in the review at the moment. I want to spend the last 10 minutes of the lecture talking about the second problem. The second problem is the self-propagation of flexible flappers. This example is loosely based on fish schooling. So, but of course, here in this case, I'm going to consider only two flappers that are swimming in tandem. The flappers are modeled very similarly as the span-wise flexible wings that we just discussed. Now, the difference is that now the flexibility is along the chord. Okay, so now this would be the chord. And what we do is we impose the motion of the leading edge. Okay, so the way in which these flappers swim is that because we impose the vertical motion of the leading edge, the rest of the flapper moves passively, and then you generate thrust, and then the flapper starts moving until it reaches the steady state velocity. And now when you have more than one, and we let them swim freely in the horizontal direction, they might adjust the relative position as a result of aerodynamic interactions. So the question we wanted to address in this study is whether there are stable configurations, and if yes, if these configurations result in energy savings for the flapper which is flapping behind. We are not the first ones to look at these problems. So there is some studies in 2D from first ones I'm aware were done by Raman and Aribo, who studied airfoils that were able to keep in motion and free to move horizontally, and they observed that the follower stabilized at quantized positions, yeah? So that there was indeed an equilibrium position. And later, after this, there were some more studies where they observed that indeed, because the Raman and Aribo didn't say anything about the energy savings, but then all the studies later on showed that indeed the follower is able to save some energy. Now, when you look at a 2D configuration, like this one, like the one studied from Raman and Aribo, the wake of the oscillating airfoil is very long, form of alternating vortices, which diffuse very slowly because there is no vortex stretching mechanism. While for three-dimensional bodies, in particular plates that we look at, the slender bodies that we consider, the wake is rather different. This is formed by oscillating by vortex rings that shed alternatingly top and bottom, and they move in an oblique direction, and they also diffuse much more quickly than the wake in 2D. So we were wondering whether for such configurations it would be also possible to obtain stable solutions. So here are a few more details about the case we are studying. So we have two flappers that are moving in tandem, as I said. So we impose the motion of the leading edge of the flappers so that with sinusoidal laws with the same amplitude, and we consider both a vertical offset, h, and a phase lag between the motion of the follower with respect to the motion of the leader. Okay. while we let them evolve freely in the horizontal direction. No? This quantity D actually is a result of the calculation. Okay. So what we do in the study is we do a parametric study in which we consider several offsets, and also we consider several values of the phase lag. And other parameters are fixed. As I mentioned before, the parametric space is huge, and all these parameters are fixed. In particular, for example, the aspect ratio of the flapper is 0.5. And all these parameters have been selected so that the propulsive performance of the isolated flapper is reasonable, so that we get a reasonable swimming speed. Okay, so let me jump into the conclusion, into the results. So indeed, we do find stable configurations, and we have found two kinds of stable configurations. We find one kind that we denote compact. Okay, and in the compact configuration, what happens is that the follower, we release the follower at some distance from the leader, but the follower approaches the leader and settles just behind the leader, so that they form sort of as a broken airfoil. Okay, so this configuration we call compact, and then there are also some other configurations that we call regular configurations, in which after an initial transient, the follower settles at some distance from the leader. In both cases, the propulsive speed that we get is very similar to the one of the single flapper. So we only observe variations in the propulsive speed of about 3%. So now, what about the equilibrium distance then? So when we plot the equilibrium distance as a function of the phase lag here, and I'm also plotting here all the values for all offsets that we consider, we observe that the equilibrium distance, all the data falls along a line, okay, and independent of the offset, of the vertical offset. So it seems that the equilibrium distance only depends on the phase lag and not on the vertical offset. Interestingly, in 2D, something similar happens. Also the equilibrium distance varies linearly with the phase lag, but the slope of this line is slightly different, and this is a fact for which we don't have a clean explanation why this happens. So this deserves further investigation. Now, what about energy savings? Do we save energy by the follower or by the leader? So in order to do that, what we do is we look at the power requirements. Okay, so we plot the power that is needed to move these flappers, and what you see here is that we do this as the product between the force on the leading edge times the velocity of the leading edge. While so we do here the maximum with this quantity and zero, because we are assuming that we cannot extract power from the fluid, so that the actuator that is moving the flapper, when this number is negative, cannot use this energy. Okay, and then we compute this number, and we compare this number to the power that we require to move the single flapper, so that when the power ratio is bigger than 1, we need more energy, and when the power ratio is smaller than 1, then we are saving energy. Okay, so here I'm plotting this power ratio for all cases. So here on the left, you have the leader data, and here on the right, you have the follower data. So here on this axis, you have the vertical offset. On this axis, you have the equilibrium distance. The data is connected by values of the same phase. So for example, this is the data for phase 180. And as I said, here we have the leader, and here we have the data for the follower. So now, when the equilibrium distance is close to 1, that means that we are in a compact configuration, okay? And in the compact configuration, we observe that we always have more values higher than 1. So that means that the compact configurations, they are not efficient. Also, we observe that the leader performance is very little affected by the presence of the follower in the regular configuration. So you see that all the data here is in white, and white means 1, so that the leader is not affected by the presence of the follower. but the follower is indeed affected by the presence of the leader. And we see a number of configurations for which we do have strong energy savings, and the energy savings do depend on the vertical offset. So we find that in order to save energy with increasing vertical offset, the equilibrium distance then needs to be larger. So you see we get this sort of trend here. We can also try to understand a little bit better why this happens. And in order to do that, let me show you the plot of the power required as a function of time for several cases that I have selected here. So the cases selected are indicated also here. So first thing you notice is that the differences are very subtle because all curves here are very similar. For example, the case of the isolated flapper is in dashed line, and that's also very similar to all the other lines. So in order to understand this a little bit better, we need to do the difference between the follower with respect to the single. So I do the difference here, and I plot the difference between the follower and the isolated, okay? And then you get these lines. And then you see that only we get savings, so we get below zero, during the second half of the stroke. So in the first half of each stroke, we always spend more energy, and we are only saving energy in the second half of the stroke. This case, by the way, is this case, which is the optimum case of all the cases we have had. So this is the one with the best performance, okay? And in any case, we see that the difference between being less efficient or more efficient happens during the second half of each stroke. Okay, and we can try to see if visually looking at the flow, we are able to understand how this happens. So what you have here now is on the left, you have a visualization of the single flapper, and on the right here, you have a visualization of the follower for the optimal case, so the case with the best performance. So here on this plot on the left, you have the pressure field on the midsection. And here, what you have is in this plane in the case with the dice line, here you have the cross flow, a visualization of the cross flow. So that you see here that in the case of the isolated flapper, very clearly you see that there are the tip vortices at the tips are very clearly visible here, okay? So now when you compare what happens in the case of the single flapper with respect to the follower flapper, so what happens is that there is a constructive interaction between the wingtip vortex of the flapper and the vortex ring left shed from the leader flapper. So that if you look at the jets, vertical jet of velocity that you get in this particular section, you see that it's much stronger, the vertical velocity in the case of the follower, and that leads to a reduced pressure on the lower surface of the follower compared to the pressure in the single case. And this constructive interaction is what explains the lower power requirement in this example. So that again, here we see, as we saw in the case of the spanwise flapping wings, spanwise flexible flapping wings, we see again that the timing of the events is extremely important in order to enhance the performance. So with this, I finished this part of the presentation, and also the presentation overall. I have shown you now a problem that combines aerodynamic interaction, flexibility effects, and coupled dynamics. We have explored stable configurations in 3D, and we have shown that indeed for some of the cases, we do have energy savings. You can have much more information in this paper, where you can also see some modeling considerations. And with this, I thank you for your attention.
Thank you very much, Manolo, for the very interesting talk after the two examples you showed. So I would say we can open the stage for questions. If there is someone who would like to ask a question, just feel free to unmute your mic and ask the question directly, or you can write in the chat and I can report the question. Let's see if there's someone. would like to start? Then maybe I can start with a question actually on your last case, but it's a question that applies also to the previous one. How robust do you think these optima are supposed to be with respect to perturbed flow conditions in which the real fish or the real dragonfly is supposed to swim?
Well, I don't know how to answer this. We are doing some studies in which we look at oscillating airfoils with incoming turbulence, and we see what we see is that the aerodynamic forces are not strongly influenced for the motions, for the strong motions that we are having. Now, of course, one could argue whether the turbulence that we are having is realistic, because the environments in which fish or dragonflies move are not uniform at all. Mm-hmm. So I would not say that the results are relevant for that condition, but what we are trying to do is we are trying to understand phenomena that lead us to some new ideas. For example, I showed in the case of the span-wise flexible wings that by analyzing the results, we were able to come up with this new hypothesis. And now it needs to be seen whether indeed by having a more rigid hindwing, in practical problems, you get better performance. That remains to be seen, of course. But at least we have developed a new idea.
Sure, definitely. I mean, regardless of the direct application, that's definitely a new regime which you uncovered. So that's out of doubt. Yeah. So let us see if there is someone else who would like to ask a question. Just once again, feel free to unmute your mic if you want to ask a question, or you can write in the chat and I can report it. Okay, that doesn't seem to be the case. Then I have another question, if I can. In the case of the two wings, actually, you presented before. I just want to ask something, because I'm not sure if I managed to understand correctly the modeling which is implemented. So you actually deform them in by torsion, but you don't have by torsional springs, yes. Mm-hmm. But you don't include like flexion moments, or they just deform basically on a plane, right? Or along an elastic line, or
sure. So there's only this flapper is only flexible along the span, indeed. So they can only let's say two of these plates, they can only rotate with respect to each other, and that's it.
Okay. So even in this case, with just basically 1 degree of freedom more than the stiff flaps, then you even in this case you manage to get quite a different regime. Okay. Interesting. Yeah, that's very interesting. Okay, so last call. If there is a part of the audience who would like to ask a question, just feel free to unmute your mic or write in the chat. well, that doesn't seem to be the case. So, Manolo, thank you very much for the very interesting talk.
Thank you for having me.
I invite our audience to thank our speaker again. Thank you. So have a good evening to everyone, and hope to see you soon next week.
Thank you, Francesco.
Bye, Manolo.